All right, so in section 3.2, we're going to talk about the line of best fit. In the previous section, we talked about the correlation, we talked about describing relationships, and oftentimes we would actually kind of either draw the line of best fit or at least think about it. So now we're going to actually talk about how to calculate that line of best fit and what is the best fitting line, I guess. So some definitions. Suppose we make a scatter plot of a response variable versus an explanatory variable. A regression line basically has the form y hat equals a plus bx. The hat is kind of important. It's red y hat, and that indicates a predicted value. So that's a predicted value or a prediction. We shouldn't write y equals a plus bx. In fact, on my test, you'll lose points for that because y does not equal a plus bx. When you use a regression line to make predictions, whenever you put in a certain x value, this is my predicted value and this is my actual value. Those are different numbers or different values. So we should have different variables to represent them. This is the predicted value. This is the actual value. Slope is b. Y-intercept is a. Why don't we use m and b? Y equals mx plus b. It's really not that big of a deal, but we don't. If we use this because if we want to higher levels of statistics, we're going to add more predictors, more explanatory variables, so we can pick different letters, I guess. Not a big deal, though. On the calculator, you can use the mx plus b, no matter. So, y actual, y predicted, done. Residuals. This is probably new for most of us. A residual is the difference between an observed value and the predicted value. I like calling it not observed, but y actual minus y predicted. A lot of kids mix up the order of these. Just think about AP. This is an AP stat class, so it's A first, P second, actual minus predicted. Graphically, your residual is basically this vertical distance between the actual value and the predicted value. Here, my residual would be positive because the predicted value is big, and the actual value is big and the predicted value is smaller. So this would have a positive residual, this would have a negative residual. But it's basically the vertical distance between the data points and your line. And it represents the error in your prediction. That's kind of why they're important. The residuals are, I want to make a prediction. My predictions are off by that much. So my residuals are actually my prediction errors. So now it's time to talk about the line of best fit. We're going to talk about the least squares regression line. This is one specific best fitting line. There are more, but it's the only one we're going to talk about in this course. It's by far the most popular. So we could look at these plots here to try to figure out what this means. Let me actually read it here. So the least squares regression line is the line that makes the sum of the squared residuals as small as possible. That's it. And that's kind of a common multiple choice question. Not on the AP test necessarily, but on my test. It's the line that minimizes the sum of the squared residuals. Residuals are my errors. I want to minimize those errors. The least squares regression line minimizes the squares of those errors. So instead of looking at this, I want to look at a more interactive picture. So this is a this is Geometry Sketchpad. It's not really a stat program, but it illustrates what I want to illustrate. So we got some data points, and I want to find the line of best fit, or I want to move my y-intercept and my slope to try to find the line that fits my data points the best. And you could try to do this or visualize it. Basically, you kind of want to go through the points as well as possible. So maybe there. But if you want to think about the least squares regression line, if I show my squares, so basically what I did was I calculated the vertical distance from my point to this point on the line. That is my residual. But the least squares regression doesn't minimize those values. It's kind of like the standard deviation. Remember when points are really far away from the mean? the deviations from the mean are really big, and we want to square those. We kind of do the same thing here. We want to minimize the squares of those distances. So it penalizes points that are further from the line. And then I want to add up the sums of these. I want to add up all these. I'm going to show the total area. This rectangle here, this number, is the sums of all these areas. So what I want to do is I want to move my line around until that sum is as small as possible. So right now I got a 9.47. Can I get it small? Oh, 9.32. 29. Oh, now it's getting bigger. But remember, I can modify two different variables here, right? 2.5. Ooh, got it to 9. So if I keep playing around with this, I can try to get the smallest value as possible. But mathematically, using calculus, I know some of you guys in calculus, you use your use the calculus to minimize a function. Well, we want to minimize the function that is the squares, sum of the squares of these residuals. It's actually a little more, it's more complicated than high school level calculus, but it's the same idea. So there is an actual mathematical line that makes this as small as possible. It's called the least squares regression line. Oh my goodness, I was way off. Should have played around with it a little bit more. But my area was 8.92. Apparently, this green line is better than 8.92, meaning the sums of these squares is going to be less. So let's see how much less it is. 8.92. Well, that's way higher, but I haven't done the slope yet. Yep, that's quite a bit smaller. 7.08. I'm a little bit off, but that line right there, you can't do it any better. Mathematically, there is no better line. That's the least squares regression line. Okay? Extrapolation, basically, if we, looks like this is miles driven between 0 and 160,000. If we make predictions within our data range for our x variable, that's making predictions within, it's kind of like called interpolation, right? We're making predictions within our data set, fairly reliable. However, if you wanted to make a prediction at 300,000 miles, far outside my explanatory data values, now you're kind of going to run the risk of they might not be very reliable. Our book says they're often not accurate. Well, sometimes they are, but maybe this relationship that was linear for these values changes, outside those values. So they're just not reliable. However, oftentimes we do want to make predictions outside our data set. That's why we're doing what we're doing. All right. This is kind of an important example. I'm going to stop the video here so I can get a fresh start on the next one. Also, we'll probably do this one in class. So thank you very much.